As a continuation of the dynamic signal sampling and understanding the different waveforms that we might experience or encounter in the real world that we're trying to measure, we're going to talk a little bit about Fourier analyses. This is covered in the book, section 4.4.3 through 4.7, if you want to dive a little deeper. As I say with almost every one of these videos, this is kind of an overview, and you may find throughout your career you may need to dive deeper than what we cover here. So what is a Fourier transform then? I like to think of it as a mathematical prism in which we can take the time domain and transfer it to the frequency domain. So then we can look at what are the most common frequencies that are found in a specific signal. So we have a square wave signal here. You can see that signal is in the time domain, and it is what's happening in real time or as we collect it in a data acquisition system. Now, we use the Fourier transform to convert it into the frequency domain, and you can see here in the frequency domain which of these is the most common or the highest amplitude of all the different frequencies. And so you can imagine this is an extremely powerful tool, and it is used in so many situations. So a Fourier transform is extremely powerful. That said, as you get into it, you'll notice that some of the math can get pretty hairy. I wouldn't be intimidated by that for this class. I try to help you focus on the concept of what the Fourier transform is allowing you to do with signals that you're collecting in the real world. Okay, so if we have a periodic function, and if you make some assumptions, we can use a Fourier series to break it into an infinite series of sines and cosines, which makes sense for us, right? If we have enough different coefficients and different harmonic orders and different fundamental frequencies of a Fourier series, we can characterize really any signal that's out there, even something that looks like this. Like if you look kind of closely, you can see that there's some level of sinusoidal component to this signal, but also you could characterize all the other signals that are on top of that. And so as we dissect this just a little bit, we notice that we've got this A naught over 2. That's really just the mean or the DC level of the signal. And so if you took kind of the mean of all these points, that's going to be a specific value, and that is essentially the DC or the direct current level of that signal. So that's going to be the mean. So as we start getting a little bit deeper, we start looking at the harmonic coefficients. And you can see that we have two different versions of these harmonic coefficients. And really the only difference is one of them is in terms of period and the other one is in terms of frequency. And so you could convert back and forth. And we'll see that in just a minute as we go through. We'll step through the frequency version of it first, and then we'll just look at the period version of it after that. So you can see what we've got going on here. We've got a function that has cosine times the harmonic order times the frequency times our time constant or time coefficient, and we are integrating that from 0 to 2 pi over omega. And so you can imagine if we knew these values of our time coefficient and our frequency, we could easily calculate what the a sub n coefficient is. And similarly, we could calculate the a sub n coefficient if we knew what the period was. So these two are going to result in the same number. B sub n, same thing. So as we go through, you can see that we can calculate out the harmonic coefficients using these equations here. And we really can represent some interesting waveforms if we run through all of these equations. And again, you can just convert back and forth with that period. So if we look at a sinusoidal waveform, that's pretty simple. We've got 349 hertz. And as we go through this 349 hertz and we run it through a Fourier transform, our spectrum that we get on the frequency domain shows that we have only one frequency present, and that one frequency present is 100% of the magnitude of what's coming in. It's a pure sine signal. Now, what if we had something like a boxcar or a square waveform with a 2 pi period? Now, we would calculate our coefficients and figure out what those are. And so we've got the A and B coefficients here. And we can convert them into something that's meaningful for this specific problem that we're working on. And you can see that if we have a period of 2 pi and we try to look at the frequency, and the frequency is equal to 1 over 2 pi, then you can see our omega naught ends up, the omega naught is 2 pi times our frequency. And if our frequency is 2 pi, we plug that in, we end up with 1. So that simplifies this down quite a bit for our frequency. So then if we plug that in and we start running through to calculate out what these coefficients are, and we could put in all these numbers and calculate out what our coefficients are. But what we're trying to find out here is what is the most common frequency that is found in this square wave. It's kind of an interesting question to think about, right? Square waves have a lot of frequencies in them, especially around this little corner right here where it's sharp. So let's go through. We calculate the coefficients. So our a sub naught is equal to a over pi, and then we start plugging in our numbers here. And if we have our a naught, which has a limit going n to 0, we can use L'Hopital. Oh man, that's bringing back some great memories, isn't it? But if we use L'Hopital, we end up with this equation right here. We plug in all of our values, and we end up with a 0 because we have 2 sine 1 times pi over 1 minus the same thing. We end up with 0. A2, same thing. We end up with 0. So all of these, you can see we've got a pattern. You could do 3 or 4 more and just make sure that that pattern still exists. But essentially our A coefficients are all going to be 0. So if we look at our B coefficients, we pull down that equation from a few slides ago, and then we start plugging in our values. We use L'Hopital again, and we end up with a 4a over pi. So we're out of luck. It did not cancel. B2, however, does cancel out. B3 does not. So every other one seems like it's not canceling out. Do you see any other patterns here? It's kind of interesting that we have a 1 pi on the denominator here, and a 3 pi here, and then a 5 pi for the 5th harmonic. So as we go through, we could extrapolate out to infinity, right? We could just keep going and we would know exactly all of the frequencies that are characterized by this square wave. So if we start collecting our terms, all of our A coefficients are 0, all of our B coefficients, we have a pattern here. That pattern, if we start plugging it into the overall governing equation from a few slides ago, gives us something that looks like this. And we can even make it more general and say all the way out to infinity, we're going to have the same pattern of 2 times n, whatever the n is at that location, minus 1, and then we do the same thing here in the frequency. So you could calculate out to infinity all of the coefficients and find out all of the frequencies characterized by this using a Fourier transform. This is really exciting. If we could do the same exact scenario, but use the period term instead of the frequency terms. And again, we're going to end up with pretty much the same equation, but we have a 2 pi in here because we are dealing with the time period in seconds instead of radians per second. Okay, so now we've got our mean value. Our mean value, that makes sense because these are an amplitude of A in the positive direction and an equal and opposite negative A in the y direction. And so as we go through here, they're going to cancel each other out and eventually end up with a DC value or a mean value of 0. So now if we look at it graphically, and we have on top of it the time domain and on the bottom of it the frequency domain. So again, the difference, what we've done here is used a Fourier transform to go from time domain to frequency domain, and we can see how many of these signals or different frequencies we have and what their amplitudes are. How cool is this? So we've got our y as a function of time, and as we plug that in, we've got 4a over pi, and then we start plugging in all these frequencies, and you can see this pattern that we have 3, 5, 7, 9, 11, 13, 15. And so as we get further and further out here, the amplitude of those other frequency coefficients is going down. So think about that for a second. What happens if we truncate this? What if we cut it off? What does that mean for the signal? So if we go back to the very beginning of this discussion and think about this is happening in the real world. We're trying to collect a signal. And that signal might be a Helmholtz generator. Do you remember one of the first classes where I blew across the top of the Coke bottle and we used it to calibrate the Coke bottle as a function of the mass of water inside the Coke bottle, we used a fast Fourier transform. And so it showed us on the screen of the Firefox app which frequencies were most common and what frequencies had the biggest amplitude. And so my whistle was the biggest amplitude because that was the highest value that the microphone could hear. Now it probably had all kinds of other stuff, like maybe a little bit of noise in the room, maybe some ambient noise, maybe the computer hum, maybe it heard the overhead projector running. You can hear my 3D printer in the background. So it would probably pick up those things, but there's such a small amplitude that it wouldn't be that big a deal for us. And so you can imagine filtration of signals. This would be very handy for if we took it from the time domain into the frequency domain, cut off any frequencies that we didn't like, and then brought it back to the time domain. You could do that. So keep that in mind for just 1 second longer. So we've got some examples out of the book. So we have some different waveforms here, and they have an equation right here. And so you could just use this equation for these different scenarios. And so depending on the frequency you had, or if you had the period, you've got the amplitude here. If you knew what that was, you could calculate all of the terms that you need to, and you could say on the 7th harmonic, we have this amplitude. Very, very handy, very, very powerful. So you can look at those in the book if you would like. So what happens, going back to this question, what happens if we truncate anything less than infinity? Well, if we think about that for a minute, that means we're getting rid of frequencies that truly existed in the real world. So number one, we know throwing away data, we got to be very cautious of it. But number two, how big of impact is that to the real signal or to the real answer? And so every time we truncate, we're going to be less and less accurate. The whole point of this class is to determine how accurate our answers are. And so the question is going to be, how accurate do you need to be? Well, we can get a pretty good feel for that. But essentially, when we truncate, the further out we truncate, the less impactful it is. So let's look at what this looks like. If we truncated down to just 3 terms, so we had 1, 2, and 3 coefficients here, this is what you're going to get. Now, the input was a perfect square wave, and the output is not a perfect square wave. You can see the slope is not straight. We also have this squiggle, same thing. But if we truncate it for 5 terms, it gets better. 8 terms, it gets better. And so how much do you want to represent that? And there are instruments out there which are looking for a specific signal to turn on and off, maybe a square wave signal. And it's going to be looking for some sort of ramp up. But if you don't have a crisp enough edge on this transition right here, it won't see it as being turned on. And so if you truncate your terms down to the first 3, and you've got an instrument that can't have a tolerance wide enough to pick up on this up, it may never show that the trigger occurred. So where do we use FFTs? Well, digital pictures, digital audio files, videos. Anytime we're doing file compression, we're using FFTs. Now you think about it for a second. If we have an FFT that we use and then we truncate it to store it, so we take all of these samples. I mean, there could be 10 million samples in this. We don't know what the sample rate was, but there could be a lot of values in here, which are going to be very expensive to store if there are a lot of them, right? So if we do a Fourier transform and then we truncate everything off, now all we're saying is we've got a frequency and an amplitude. That is far less expensive for us to store. However, if you truncate it off and then you take it back into the time domain, what happens? Well, now it's not going to reflect reality quite as well. So you've probably listened to an MP3 file or maybe a video before where it's not as good as the original. And that's probably what's happened, is it probably was compressed using an FFT, and then things were truncated off of it in order to compress it and make it much smaller to transmit via text or whatever. And then you decompress it, and when you're decompressing it, you just don't have that information. It was truncated out. And so you don't know all those other frequencies that should have been included. And so then you lose fidelity in that original signal. All right, I'm going to play this. Now it can be a little bit annoying. I don't know if the sound will come through on the recording. I would suggest you play this, but some people, when I do it in class, some people don't like it. So let's listen to this and see what we get. So let's start this over at the beginning. So right now, there's just a pure sine wave in here, and you can see that because it's not an electronic exactly pure sine wave, we've still got some of these other coefficients happening, and so this is not mathematically a perfect sine wave. It is a tone, and so there's a few other things that we're picking up. But as we add different frequencies to it, you'll see exactly what we've been looking at. So we've got these third, fourth, fifth harmonics that are happening, and now we're getting closer and closer to a square wave. And so this is what's happening electronically. This is where people usually start cringing in class. And if you're over 40, you probably don't hear this last one. I can't hear the change there. Okay, so that gives us a pretty good idea of how the FFT is used and how some of the applications that we can use in FFT. Again, extremely powerful, used everywhere. Now, there are some additional bits of information, trig relationships here at this website, or I've got a few more out of the back of the book. So, and that's to help you with the math side of it if you do need to get there.